The median. So when we're looking at various density functions, one of the measures that's often useful for us is to figure out the average value for a distribution. There are two ways in which we find average values for a distribution, and the first one we're going to look at today is called the median. You may have heard of the median when looking at data sets in other courses. It's the same idea here, only now for the median, we're looking at the weighted distribution. So let's see how that works. So a median of a quantity x distributed through a population is going to be the value t such that half the population has values of x less than or equal to t, and half the population has values of x greater than or equal to t. So when you visualize what's happening with the median, we're trying to figure out the place where half the area under the curve is on one side of our median and half is on the other side. And so if we have something that looks like this, our median might be roughly here because this half of the area is the same as this. So 50% to the left, 50% to the right. So we're trying to find that x value where exactly half the area under the curve, or 50% of the population, is to the left and half is to the right. So if p of x is our density function, then our median has to satisfy that when you integrate from the lower bound up to t, you get 50% of the population. So that represents the left-hand side. And ultimately, if that's 50%, then the other side also has to be 50% because we know that the area has to add up to 100%. Equivalently, if we had the cumulative distribution function already, that would be equivalent to setting the CDF equal to 0.5, because again, the CDF is the accumulated amount up to a point, and so if that's 50%, that is the equivalent statement for CDFs. So let's go ahead and look at what we can do here by using what we know about density functions and CDFs in general, and now tying in this idea that we want to be exactly half of the population on the left and half the population on the right. Example 1. Given the density function below, find the median. So here we have a picture of a density function, and we don't actually have the formula of the function, which is something that we need in order to be able to find the median. So our first step here is going to be to find the equation for the density function so that we can then apply what we know about the median. So on this picture, we have 2 points. And so the first point is the point 0, 1. And then we also have the point 2, 0. So that's what we need to find the equation of a line. If we have 2 points on the line, we can use that to find the equation of the line. So here, I'm going to start by finding slope. So on the top, I have 1 minus 0. On the bottom, I have 0 minus 2, which gives me a slope of negative 1/2. Now, remember, the equation of a line is y equals mx plus b. We just solved for the m. Your b is going to be your vertical intercept. So where does your line cross through the vertical axis? There's 2 ways to solve for this. We can do it visually. We can see that it crosses through at 1, or we can plug in one of our points. Either way, we're going to find that b equals 1. So that means that the equation of my line and my density function is given as negative 1/2 x plus 1. So now that I have my function, I want to use what I know about medians to figure out where half of the population will be to the left and half the population will be to the right. So if I was going to guess, right, so this is 1. It's not going to be at 1 because if I drew it at 1, then the triangle to the right of 1 is certainly smaller than the trapezoid to the left of 1. So I'm going to guess that it's somewhere to the left of 1. I'm not sure exactly where yet. So let's go ahead and set up our equation to solve for the median. So our general equation here that we're going to set up, we have the integral from the lower bound, which is 0, up to t. That's what we're solving for. And we're integrating our density function. and finding out where that equals 0.5. That's what we're trying to solve here. So what I'm going to do is I'm going to solve that antiderivative by hand so that I can plug in my bounds so I can get that t into something that I can solve algebraically. So when I solve the antiderivative here, I get negative 1/2 x squared over 2. So I add 1 to the power, divide by the new power, plus, now the 1 is going to pick up an x, and that's going to be from 0 to t. Right now I'm just finding my antiderivative, and once I have that, I will set it equal to 0.5. So now notice here that this fraction can be simplified a little bit into x squared over 4 with the negative in front. So I have negative t squared over 4 plus t, when I plug in my upper bound, minus 0 plus 0, which is 0. So I get an antiderivative of negative t squared over 4 plus t. So now I need to figure out, when does that equal 0.5? So I have to do some algebra here, right? This is going to be a quadratic. So I have negative t squared over 4 plus t equals 0.5. Because I have a quadratic equation here, I want to solve this using the quadratic formula. In order to do that, I need to get everything on one side of the equation. So this goes back to algebra. Hopefully this sounds familiar. So I'm going to bring both of these terms over to the right. So I have 0 equals 0.5 minus t plus t squared over 4. So I don't like fractions when I'm trying to solve the quadratic equation algebraically, so I'm going to go ahead and multiply through by 4. You don't have to do that step. You can certainly keep solving with fractions or decimals, but I prefer to get rid of them. So if I multiply everything by 4, I'm going to get 0 equals 2 minus 4t plus t squared. So now everything's in terms of integers, which is nice. I'm going to use my quadratic formula, which is the opposite of b, which is 4, plus or minus the square root of b squared, which is 16, minus 4 times a times c, which is 8, all divided by 2a, which is 2. So there's 2 roots here, right? I have to solve for the plus and for the minus. So the 2 roots I get when I solve for each situation here, it's going to give me either 3.4142 or 0.5858. Now, remember, on our density function up here, we were only defined from 0 to 2. So that means that the 3 doesn't make sense. The one we're looking for has to be between 0 and 2. So 0.5858 is going to be the point where half of the fraction of our density function will be to the left and half will be to the right. So that's a little bit past halfway. So I'm going to label that here, 0.5858. And we can see now that our median is going to have half our population to the left and half to the right. So that means this area is 50% and this area is 50%. If I wanted to check to make sure I'd solved correctly, what I could do is I could set up an integral from 0 to 0.5858 of my density function, negative 1/2 x plus 1, and that should equal something really, really close to 0.5. Now, I rounded my median a little bit because it was a little bit longer. I rounded to 4 decimal places. So I'm not going to get exactly 0.5, but I'm going to get 0.5000 something something. So that's close enough. So I can check this on my calculator to make sure that I solved correctly for my t. So there's one example of how we would do this. Let's look at another. Example 2. Suppose that x measures the time in hours it takes for a student to complete an exam. The probability density function for this distribution is represented by little p of x equals x cubed over 4 if x is between 0 and 2 and 0 otherwise. So we can tell that this exam is only given 2 hours because all students have to finish between hour 0 and hour 2. Otherwise, there's a 0 probability because students aren't taking exams outside of that. Part A asks what is the probability that a student picked at random completed the exam in less than 1 hour. So remember, with probability density functions, we're still looking for the fraction of the population because that tells us the probability that the event occurs within that time frame. So here, less than an hour means we need to integrate our function from 0 to 1, x cubed over 4 dx. So this is a definite integral. Both of the numbers on the bounds are numbers. There's no variables there. So we can plug this into our calculator. So here, if we plug this in, we get 0.0625 or 6.25%. So about 6% of these students complete the exam in an hour or less. So it must be a little bit of a difficult exam here. Not many students are finishing. So the median time, part B, we will expect to be more than 1 hour, somewhere between 1 and 2, because we know that all of the area we've accumulated up to the 1 hour mark is only 6.25%, and we have to get all the way up to 50%. So we're expecting our answer to be between 1 and 2. So the median time says that we're going to go ahead and go from the lower bound, which here is 0, up to t of our function, x cubed over 4 dx, and we want to know when does that equal 0.5. So again, I'm going to start by finding my antiderivative. So I'm going to add 1 to the power and divide by the new power. So that's going to give me x to the 4th over 16 from 0 to t. When I plug in a t, I get t to the 4th over 16 minus 0. So my antiderivative is t to the 4th over 16. So here, I want to know, when does that equal 0.5? So at what value will I get 50% of the population? So if I set t to the 4th over 16 equal to 0.5, notice here that there's only one t on the left. In the last problem, we had more than one t, so we had to approach it algebraically differently than we will in this problem. Here we can solve directly for t. So I'm going to multiply both sides by 16, and that leaves me with t to the 4th equals 8. Now I'm going to take the 4th root of both sides on my calculator, and when I do that, I'm going to get that t equals 1.68. So that means that I'm taking about an hour and 40 minutes, roughly. So 1 hour and then 0.68 of an hour. So 45 minutes would be 3/4 of an hour, so 0.75. So a little less than 45 minutes. But it's happening between hour 1 and hour 2. So 1.68 is when 50% of students have finished their exams, and then the other 50% are going to finish between 1.68 and 2 hours. Let's look at another example. Example 3. Let t days be the length of time a pair of jeans remains in a shop before it is sold. The density function of t is graphed below, and the density function is given as 0.04 minus 0.0008t. The first question is, what is the longest time a pair of jeans remains unsold? So looking at our graph, we can see what the bounds are here. They go from 0 to 50 days. So at 50 days, that is the last possible time that a pair of jeans is sold. That's the longest it will be, After that, the probability is 0. So all of the genes have been sold after 50 days. Part B. Would you expect the median time till sale to be less than, equal to, or greater than 25 days? So 25 days you can see is marked on our graph here. If I look at 25 and I envision the triangle to the right of 25 and the trapezoid to the left of 25, the trapezoid has significantly more area, which means that it's not going to be balanced. I'm not going to have a 50-50. So I'm expecting it to be less than 25 days, because in order for it to be balanced so that the same amount of area is on the left and the right, I'm going to need to be left of that 25 mark. Part C. Find the median time required to sell a pair of jeans. So I'm expecting something between 0 and 25. And again, I'm going to set up my integral from 0 to t. So 0 is my starting point here of my density function, 0.04 minus 0.0008 t dt. I'm going to find my antiderivative first, and then I'll set it equal. So here, my antiderivative, I'm going to have 0.04 t minus 0.0004 t squared from 0 to capital T. So the second term was t squared over 2. So I divided the 0.0008 by 2 to combine my constant. So now, when I plug in my capital T, I'm going to get that my antiderivative is 0.04 capital T minus 0.0004 capital T squared minus 0, because when you plug in a 0, everything is 0. So my antiderivative looks like this. And I want to know, when does that equal 0.5? So again, I have more than one term with t here. So I'm going to have to use a quadratic equation. So I want to bring all my terms to one side. So I'm going to bring these two terms to the right, but you could certainly move the 0.05 to the left. It's just a matter of preference. So I have 0 equals 0.5 minus 0.04 t plus 0.0004 t squared. So now I have to do the quadratic equation. I could certainly multiply everything by 10,000 if I wanted to not deal with decimals here, but then I'll have some pretty huge numbers anyway. So I'm going to go ahead and just deal with the decimals in my calculator. So my roots here are going to be the opposite of b, so positive 0.04 plus or minus the square root of b squared, so 0.04 squared, minus 4 times a, which is 0.0004, times c, which is 0.5, all divided by 2 times a, which is 0.0004. I have to do both the plus and the minus case. I'm going to do this very, very carefully in my calculator. And when I do, I get t values of 85 or 14.64. So again, to figure out which value is my median, I need to see which one of these two numbers is on the interval that I'm considering. So 85 or 14.64. Let's go back to our picture. So according to our picture, our PDF only exists from 0 to 50. So that means that the 85 does not work. Instead, the 14.64 is going to be exactly where our median is. So here, remember that t is in days, right? So sometime during the 14th day is when exactly 50% of all genes are left unsold. And the rest of them all go away by the time we get to 50 days. So the median here is 14.64 days. So let's try one more example to make sure we understand how to compute the median. Example 4. A quantity x is distributed with density function p of x equals 0.5 for x between 0 and 2, and it's 0 otherwise. Find the median of x. So this one looks really simple on the surface, and the calculations are pretty straightforward. It turns out that when you have a density function that is a constant, some interesting things happen. So we're going between 0 and 2 for our density function, but in order to find the median, we want to start at the lower bound and go up until t. So our function here is 0.5 dx. So that means our antiderivative is 0.5x from 0 to t. So when we plug in our upper bound, we get 0.5 t minus 0. So our antiderivative here is 0.5 t, and we want to know when does that equal 0.5. So here, my t is going to equal 1. Now I want you to notice that my bounds here are 0 to 2. So in this case, exactly halfway in my interval is when exactly half the area is on the left and half is on the right. And that's because my density function is a constant. So let's just remember what this would look like. So 0 to 2, I'm just constant. At 0.5, this is my 2. So all outcomes are equally likely. So that means we just have a rectangle. When your density function is a constant, that means that the area is just a rectangle. So half of the data will be exactly halfway between your interval, so at 1. So it's pretty simple to calculate, but it's interesting that this happens when we have this constant function. So keep that in mind. If you encounter other density functions that happen to be constant, you know that your t will be exactly halfway in this interval.